Good afternoon, class. Welcome back. Professor Volk here. Sorry I couldn't be with you today, but hopefully this lecture will get you through. I hope the quiz went well for you. We've discussed in Chapter 5 the terrestrial planets. We've talked about pretty much everything we need to about Mercury's internal composition, its surface, its history, the interesting interaction between its day length and year length. We've talked about Venus, Venus's odd spin. We've talked in general about its thick, hot atmosphere. We've talked about its surface features, the lack of any evidence of tectonic motion, the evidence, confusingly, that although there don't appear to be tectonic plates on Venus, we do have volcanoes, we do have lava domes, we do have these large coronae marking upheavals in the surface, which certainly seem to imply some sort of geological activity that's still going on today. And we've talked a bit about the internal structure of Venus. We've talked about the features on the surface of Mars, the smooth, low elevation northern hemisphere, the higher elevation, cratered and hilly southern hemisphere. We've talked about the Tharsis bulge area where the planet is bulged up, apparently from geologic activity in the distant past. We've talked about the 4 volcanoes on the surface and the Valles Marineris, the large canyon system on the surface of Mars. We've looked at images of features that suggest the existence of running water on the surface of Mars, and we ended up with this slide. On the left, a crater wall that is worn away, that has little grooves and gullies going down the wall of the crater to the sand dunes beneath. Looks exactly like the kind of erosion process that we would expect on the Earth. And then on the right-hand side there, an image from the Mars Reconnaissance Observer of a crater. We're looking at the upper left quarter of the crater in both images. One image taken in 1999 shows no features on the sand slope going into the center of the crater. In 2005, we see this light-colored streak as if something had melted and dribbled down the slope. That's still circumstantial evidence for us. That looks like something melted and ran down the slope, but it's really not enough to nail it down for sure. And so, again, that's not exactly a smoking gun. We have various and sundry stuff, mostly chemical composition of the rocks. This is a picture of the landscape of the Opportunity rover. I'm sorry I'm not able to show you this live in class. If you go to the Wikipedia entry for Opportunity rover and look at the, I believe it's the mission timeline page on Wikipedia, has this image and a lot of other images in extremely high definition. High definition in the sense that you have to like pan right 5 times on your computer screen to see the whole thing. This is a kind of a wraparound image of Opportunity looking at a crater. I'm pretty sure that this is the Endeavour crater, but I could be wrong on that. I should have looked it up. Anyway, Opportunity, as we said, was launched initially on a 90-day mission. Landed in 2004. It's been operating continuously on the surface of Mars for over 10 years. Still going now. One of the most successful satellite missions that we've ever attempted and accomplished. Opportunity's learned a lot about the surface of Mars, about the topography of Mars. It's an advanced rover, has an extendable science package, not nearly as big as Curiosity's, but big nonetheless. Has a little binocular camera up above the satellite, and has traveled a very significant distance over the Martian surface, much farther than we ever imagined it being able to go. A little bit more on Opportunity in just a moment. This is a very important picture. It goes in with the picture that we saw earlier from the Phoenix lander. If you'll remember, the Phoenix lander was the one that landed near the North Pole, dug up little scoops of dirt for analysis, and exposed this whitish ice at the bottom of some of the trenches that it dug. And by watching the rate of evaporation of that ice, scientists were able to definitively prove that the ice had to be water ice, that it would not evaporate as fast as it did if it was the more common carbon dioxide ice found on Mars. And so this was direct evidence for frozen water under the Martian soil. This is an image from Curiosity. Curiosity was launched and landed on Mars in December of 2013. It's a very large satellite. That's the one we said is about the size of a small SUV. Has a 80-pound science package on the end of an extendable arm, great big death laser in its head, all sorts of nifty stuff like that. Curiosity landed in a large crater that surrounds Mount Sharp. Mount Sharp is about 4 kilometers high, has a lot of interesting cliffs around the side exposing different layers of Martian rock in different geological ages. And so studying that mountain as Curiosity attempts to climb to the peak is going to be very interesting from a scientific standpoint. The crater is particularly interesting because it was believed, based on its location near some of those flow channels that we saw before, it was believed that the crater might have been filled with water at some time in the past, and that if a lot of these streams and things were being, or the stream-like features, I should say, were being made by running water, it was very possible that the crater would have been filled with water at one point. This image came relatively soon after Curiosity got started and started going around. You can see from the scale that little bar is a centimeter long. That means that this picture is about a foot on a side as far as what it's looking at. What you see is a darker patch of fine silt and gravel on the left-hand side. And then just just to the right of that, there's a shelf that goes up, and then there's an overhang of kind of crumbled rock, and then there's this more dusty surface on top, and then there's this circled, or rather ellipsed, knob-like feature at the top. Looking at this in detail and looking at the area around it, it turns out there's really only one conclusion to draw, and that is that the silt, the fine silt and the gravel, were carried by running water. Running water was washing here kind of from the upper left towards the lower right, and then running into this little ledge. When it would run into the ledge, the flow would slow down and sediment would drop out, just like it does on Earth. And so this is a very familiar pattern. As it did so, it would wear away the little shelf here that it was hitting, and so it wore away that surface until it had that overhang. And if you look, and Curiosity has looked at the chemical composition of this, and there are chemical deposits all along this area that would only exist if the rock had been in contact with water. So there's not only the circumstantial evidence of this sedimentation and the erosion of this shelf, there's also evidence in the chemistry, and in this little knob that's been circled on the upper part of the image was apparently out of the water. The water never rose high enough to submerge it, and so it doesn't show the chemical changes that it would have if it had been in contact with water for a long time. Right around here, the water would have been about knee deep, and it would have been flowing, as I said. And so this was a very significant early find in Curiosity's explorations. Yes. So that's an interesting exploration of the Mariner Valley. Of course, all of that was generated by computer uh, analyzing the topography that was shown in the MRO data and putting it to really cool music, don't you think? Anyway, so that's very interesting and a nice look at an important surface feature on Mars. Okay, we spent a little bit of time here talking about the atmospheres of Venus, Earth, and Mars, and why they're different. Then I have another couple of nifty movies for you, so a little surprise at the end. Um, we've seen this slide before talking about the internal structure of the Earth, Mercury, Moon, and Mars. Of course, on the Earth, the Moon, and on Mars, we've landed on Mars, and so we do have some seismological data from Mars. We have a more detailed picture of the interior of those planets because we have this seismic information. Mercury, we're just kind of guessing, but we're getting that info from the magnetic field. Inside Mars, you can tell that the core seems to make up much less of the volume, natural, since it's cooled off quite a bit since its formation. Also, it doesn't show as well on this image, but the crust of Mars is much thicker than the Earth's crust. Again, just like we discussed for Mercury and the Moon, the Mars is a smaller planet, and so the way the surface and the volume work out, it will cool off much more quickly than a large planet like the Earth or Venus. So Mars has radiated a lot of the heat of its formation to space, and so the crust has gotten relatively thicker, creating these extinct volcanoes. The Earth and Venus have active volcanoes and active geology, and so we can assume that that both Earth and Venus have the Earth has a relatively mild greenhouse effect. We've talked about this graph before. Visible and ultraviolet light from the sun come down. Some is reflected off of the surface of the clouds. The rest goes into heating up the surface. Infrared coming from the sun may get absorbed in the atmosphere on the way down, and then the warmed up ground radiates infrared due to the thermal emission processes that we discussed in Chapter 2. And so the infrared from the sun and the infrared being radiated from the warm Earth beneath goes into the atmosphere. Some of that will not get absorbed by chemicals in the atmosphere and will be radiated to space, but a lot of that energy is absorbed mostly by carbon dioxide, also by water vapor and methane to different degrees. And so that heat energy stays in the atmosphere and moderates our temperature, so that on the Moon you have temperatures going from 250 degrees Fahrenheit to negative 250 degrees Fahrenheit. Right next to that on the Earth, you have temperatures that that might average about. I think the global average surface temperature is 60 degrees. But between a day and a night, we might change temperature by as much as between a low and a high of 20 degrees Celsius, 30 degrees Celsius, different, like 70 degrees to 40 degrees is about what we're having right now. Much, much smaller variation than you have on the Moon because we have the greenhouse effect to balance things out. That's what works on the Earth, and that stays in a nice, convenient sort of a balance because there's two processes at work. On the one side, you have volcanoes putting out carbon dioxide. Those volcanoes emit carbon dioxide into the atmosphere. We have open water on our surface, and there's in chemistry, if you have a gas in contact with a liquid, some of the gas will dissolve itself into the liquid. That's how fish breathe in lakes. You got oxygen in contact with the surface of the lake. Some of the oxygen gets dissolved in the water, and then the fish are able to breathe that. Otherwise, the fish wouldn't have anything to breathe. They do breathe oxygen in their gills. And every once in a while, something will get thrown off. You'll get a bacterial bloom or exceptionally cold weather. The dissolved oxygen in the water will drop, and all the fish in Lake Hollingsworth die and smell really, really bad. So this carbon dioxide in the atmosphere is absorbed by the open water in the ocean. Carbon dioxide gets dissolved in the ocean in the same way carbon dioxide gets dissolved into Coke or Pepsi. The carbon dioxide dissolves itself into the ocean. A lot of it goes into the form of carbonic acid. And then sea creatures use the carbonic acid, take the carbon, obtain calcium from other sources, and create calcium carbonate. Calcium carbonate is basically the material that seashells are made out of. And when the animals die, these pile up on the bottom and they get squished together as more and more piles on. And that makes limestone rock, which is really the only kind of rock we have in Florida that doesn't come out of a concrete bag. The limestone then can get pressed down if it forms near, say, California in one of these big trenches, or if it gets carried to one of these places later on. That limestone can actually get pushed back down into the mantle of the Earth, where it will then melt, and that carbon might become available to leak out of a volcano again someday. But there's a lot of rock down there, and so the volcanoes keep going because the Earth's interior is molten. And so on the Earth, we have this carbon dioxide being injected into the atmosphere and then taken out of the atmosphere by the oceans. Along the way, some goes into plants and generates oxygen, but this isn't as significant an effect as the oceans are. So what happened different on Venus? Venus has a much denser atmosphere. It's much hotter. It's all carbon dioxide, and there's a whole lot of it. As we discussed, the atmosphere of Venus has 90 times the surface pressure of the Earth, and so it's like being 1 mile under the ocean. That kind of pressure of gas weighing down on top of you from Venus's very thick atmosphere. You got a real thick atmosphere. It's all carbon dioxide. It's no big surprise that that results in an atmosphere that has an almost perfect greenhouse effect. The clouds have become so reflective at the top that a lot of the incoming sunlight is reflected away, but the atmosphere is going to absorb infrared coming from the sun. Any incoming sunlight that makes it through is going to heat up. Basically, Venus is covered with a big giant blanket that doesn't let any heat out, and so the atmosphere of Venus gets warmer and warmer and warmer, making its surface temperature 730 degrees Kelvin, which, as we said, is over 900 degrees Fahrenheit. This creates that very unfriendly atmosphere. The clouds on Venus actually only go down to about 30 kilometers, 20 miles above the surface, and so you can't actually see detail. That picture that we saw from the Soviet Venera 9 spacecraft, you can actually, that's a fisheye lens picture, you can actually unwrap it to get a decent view of what it would look like on Venus. You can see a long way, but the clouds prevent you from seeing outer space, and vice versa. We can't see the surface. And it's just not worth the money to go there anymore. What happened on Venus? Venus is about 0.7 astronomical units from the sun. That means that Venus receives twice as much solar radiation as the Earth does. So Venus has a natural tendency to be hotter. The carbon dioxide that came out of the volcanoes on Venus immediately had more heat to grab onto and hold close to the planet. Any water vapor that got put out by Venus probably did not have the chance to form liquid water on the surface. That water was kept in vapor form, and actually a lot of the water will have reacted with the sulfur dioxide and other sulfurous compounds that come out of volcanoes to make the sulfuric acid that we mentioned is in Venus's atmosphere. And so Venus, once its greenhouse effect got started, it kept getting bigger and bigger and bigger. The volcanoes put out carbon dioxide. There's no ocean to soak it up, and so the planet just gets hotter and hotter and hotter until it, gets about as hot as it ever can. And so that's where Venus is now. We describe Venus's situation as being a runaway greenhouse effect because the carbon dioxide built up a heat so great that you couldn't form the liquid water that would take it back out of the atmosphere. Okay, so there's a situation on Venus compared to Earth. You've got the volcanoes doing their job, putting out the carbon dioxide. You don't have an ocean to absorb that carbon dioxide, so it builds up in the atmosphere. Martian atmosphere. Mars has a thin atmosphere, but it is made completely of carbon dioxide. The Martian atmosphere is about 1/1000th of the Earth's atmosphere or atmospheric pressure. So it's a relatively thin atmosphere, but it's almost completely carbon dioxide, and so there is actually a significant amount of total carbon dioxide compared to the amount that the Earth has. And so Mars does have a mild but noticeable greenhouse effect. The temperature does go back and forth in a range of about 100 degrees Celsius on Mars. The warmest it ever gets, Mars is 1.5 times as far away from the sun as we are, and so Mars only gets half of the solar radiation that we do, and so it has less energy available. But this greenhouse effect does allow the surface temperature to get just around the melting point of water in the highest, hottest summer areas on Mars, and then it'll sink down to about -150 in the coldest areas. But day to night, Mars does spin at about the same rate the Earth does. The Martian day is about 4 minutes shorter than an Earth day. You don't freeze to death as you go around the backside and go into nighttime. The greenhouse effect is enough to moderate the temperature and hold some heat close to the planet. So Mars's problem, what happened to Mars? Mars started out with this carbon dioxide, started out with water vapor that, based on what we've seen from Curiosity and the other probes, did definitely create large amounts of liquid water on the surface. But about 1.5 billion years into its evolution, the volcanoes on Mars shut down. Because of the crust getting cooler and thicker and more solid, that geological process stopped. You were no longer putting carbon dioxide into the atmosphere. You no longer had a source of carbon dioxide. Carbon dioxide that was left, some of it could have gotten absorbed by the liquid water in the Martian oceans, but honestly, the temperature would have dropped off pretty quickly, and so the oceans would have mostly frozen. Most of the carbon dioxide has been lost to space, as we discussed. Mars has about 38% of the surface gravity of the Earth, and so it doesn't have nearly as strong of a gravity field. Carbon dioxide is a great big heavy molecule, but over the intervening billions of years, most of the carbon dioxide is leaked away to space. And the water, we saw, and down there at the bottom, there's a small version of that picture from the Phoenix lander. The water froze, became a layer of permafrost, mix of water and soil together under the surface. It's gotten covered up with dust over time. We believe that in most areas on Mars, or many areas on Mars, there's ice under the surface of the dust. We think that there are places where it's warmer under the ground, and where this stuff can melt and form liquid water deep underground. Possibly not so deep underground. One of the next NASA missions that's being planned for Mars is to send up a great big drill to drill down and try and find some of these pockets of wet, moist Martian soil. And so, that's the answer to the question of why these three planets developed such different atmospheres. You've got kind of a papa bear, mama bear, baby bear thing going on. Venus, very close to the sun, had a lot of solar energy available. Its carbon dioxide developed a greenhouse effect, and that greenhouse effect went out of control, built the planet up hotter and hotter and hotter, evaporated the water in the oceans, and so then there was nothing to hold it back. It just kept on going and going, making a planet that was, in the words of in the words of Goldilocks, much too warm. Mars, on the other hand, had the opposite problem. The volcanoes shut down and were not putting enough carbon dioxide into the atmosphere to keep things warm. That caused the liquid water to freeze. Over time, the carbon dioxide leaked away to space, making Mars like mama bear Goldilocks would describe Mars as being much too cold. On Earth, we're lucky to have a balance between the two. You have volcanoes putting carbon dioxide out. You have oceans absorbing the carbon dioxide. So everything's in this nice, neat balance, and we have a temperature that stays at a level that's conducive to life, that keeps liquid water present on the surface, and so that would be like Baby Bear. The Earth is just right. So now we understand a little bit more about the atmospheres of the terrestrial planets and why these very similar planets seem so different. Okay, that concludes the main information of the chapter. We got a little bit of time left, I think. 30 minutes on my clock, and so we should have about 15 minutes left. I'm going to use 10 of them, leave ourselves a little safety factor to show you some things. One thing, as I'm recording this, I just saw this smoke trail from the latest SpaceX launch. There was a launch today attempting to, they were boosting a satellite into orbit, and they were going to attempt to recover the rocket. We had watched that animation of the Falcon Heavy Lifter with the reusable rockets that fly back home and land. They were going to try that. They decided not to. Apparently, they were going to land on a ship in the ocean, so that they didn't hit anything important, and the weather was just too bad there. They decided they'd kind of sort of try, but they didn't. They wouldn't destroy the ship. They were pretty sure that the rocket would not land successfully on the ship. In the long run, they're not going to land on a ship. They're going to land on land. That'll be nice. But that's a really cool thing in the news. We'll know more about that actually tomorrow if you've seen the news, or go absolutely see the news and see what SpaceX did today, Wednesday. In the meantime, I'd like to show you two really neato things, and I describe this first video as the second coolest way to land a spacecraft on a planet. Okay, let's have a look at this. Okay, so that is how we landed the Spirit and Opportunity rovers on the surface of Mars with airbags and lots of bounces, which is definitely a really cool way to land on a planet, especially when you can take a selfie. This is an image from the Mars Reconnaissance Observer looking down on the landing site, and you see here that the heat shield dropped off first, landed over here. The back shell and the parachute, after they let go of the bouncing airbag rocket, landed over here. This is where the airbag hit in that first bounce. Then it went dump, 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 and there is the lander itself. And so that's how we landed Opportunity on the surface of Mars. Why did we have to go through all this trouble when we don't have to do it on the Earth? The atmosphere of Mars is very thin. We can't slow down fast enough. We can't slow down to a very slow speed using just a parachute. So that's what we have to do. Now that brings us to the question of, if that's the second coolest way to land on a planet, what's the coolest way? The same very excited people that were in the last exciting NASA video are actually in the next one, and they say some of the same things. But the story at the end is pretty cool. And look at how we launched and landed the Curiosity rover. I want to point something out that is not in these videos. That little disky thing that comes towards Mars and drops the rover down. That's all that leaves Earth orbit. There's not any big rocket on that. When you leave Earth orbit, you are aimed at your landing site on Mars. And in the case of Curiosity, the lander was going to land within an area about the size of Polk County. Okay? So we're leaving Earth orbit. We're traveling 9 months, crossing almost an entire astronomical unit of distance, with one slight mid-course correction with just a little bit of rocket fuel, not very much, and we're landing in a spot the size of Polk County. And actually, even a lot more accurate than that is what we hoped, and is the way it actually turned out, to land right in this crater, right in the middle of a crater, next to a mountain. Okay, this is how we do it. August 2012. Why was I thinking December 13? Well, okay, August 2012. Um, did you notice some of the guys are the same and they look older, but they added some new people, which is all very nice. Um, but I think you'll agree that's a pretty cool way to land a satellite, or in this case, a robot, on the surface of another planet, and we did it. And it worked, and the robot's been driving around and finding out nifty stuff like the picture that we saw, all kinds of other cool stuff. Anyway, hopefully that was interesting. We're probably getting up towards the end of the period, so I'm going to cut it off here.